Okay, quiz 14.1 has to do with reaction rates and rate equations. For all the questions in this quiz, we're considering the reaction A plus 2B forms 3C. And that means that the rate is going to equal 1 over 3 times the change in the concentration of C over the interval of time. And we've got some graphs here. And so these graphs are given under 3 different conditions. The initial concentrations of A and B are given at the top of each of those 3 graphs. And the question 1 is, from the data in the graph, estimate the average reaction rate over the first 20 seconds of each trial. And that means that for all of these, our delta T is going to be 20 seconds. And we really just need to figure out what is the change in concentration. So for this first one, it looks like at the 20-second mark, we have about 0.00038 molar concentration. It goes from 0 concentration at time 0 up to this concentration at time 20 seconds. And so we'll divide that by 60 seconds. That's the 3 from the stoichiometric coefficient times the 20-second interval. And this is going to give us a rate of 6.33 times 10 to the negative 6th molar per second. If we look at trial 2 at 20 seconds, it looks like it's about 0.0015 molar. We'll divide that by 60 seconds. And this gives us a rate of about 2.50 times 10 to the negative 5th molar per second. Okay, and for the final one, it's about 0.0029. We'll divide that by 60 seconds. Falls just short of that 0.003 mark. And this is going to equal 4.8 times 10 to the negative 5th molar per second. All right, so that is the answer to question 1. Finding the average reaction rate over those initial intervals. So can we find the reaction order for both of the reactants and the overall reaction order based on these numbers? I'm going to go ahead and erase this up here. Remember, the idea is that we're going to take rate 2 and divide that by rate 1. And what's rate 2 equal to? Well, that's the rate constant times the concentration of A raised to M times the concentration of B raised to N, and under conditions for trial 2. And then we'll divide that by the rate constant. We'll divide that by rate 1, which is equal to the rate constant times concentration of A raised to 1 under the concentration conditions of rate 1, and B raised to the N of rate 1. Now, if we cleverly choose our conditions such that concentration of B is the same for both trials, then that cancels out. Rate constant is the same for both of them, and that cancels out. So we end up with is rate 2 over rate 1 is equal to concentration of A2 over the concentration of A1 squared. So if we look at trial 1 versus trial 2, we can see that the concentration of B is the same and the concentration of A is doubled. And so, oops, it's not squared, it's raised to the power of n. I apologize. Okay, so comparing trial 1 and trial 2, we see the concentration of A is doubled. So the right side of this equation becomes 2 raised to the mth power, m. And then if we take 2.5 times 10 to the negative fifth molar per second divided by 6.33 times 10 to the negative sixth molar per second. That's rate 2 over rate 1. Well, rate 2 over rate 1 works out to be 3.95. Well, that's mighty close to 4, and 2 squared equals 4. We know m needs to be an integer, so it makes most sense that we have as a rate law that the rate is equal to k times a squared, that m is equal to 2. And then if we compare trials 2 to trial 2 to trial 3, you can see that in trial 2 and 3 we have the same concentration of A, but we've doubled the concentration of B. And so we essentially have the exact same sort of an equation, only it's B to the n instead of A to the m. So let's just erase this. We would have 2 to the nth power because we have doubled the concentration of B this time. And that's going to be our rate 4.8 times 10 to the negative fifth over 2.5 times 10 to the negative fifth. Comparing rate 3 to rate 2 and concentration 3 to concentration 2, and we get this. So 4.8 divided by 2.5, that's going to equal 1.92. Again, it needs to be equal to 2 raised to some integer power, and so within that constraint, this is really most close to 2, or in other words, n equals 1. And that means that our rate law is now complete with rate equals k times a squared times b. Okay, so for question 3, we're going to give the value for the rate constant with appropriate units. So let's erase all of this. Now that we have a valid rate law, we just need to plug in values from one of our 3 trials. Let's just choose trial 3 here. So the rate is 4.8 times 10 to the negative fifth molar per second, and that is equal to our unknown rate constant times the concentration of A squared, so that would be 0.0200 molar squared, and times the concentration of B, which is also 0.0200 molar. This time it's raised to the first power. So we can just divide those over. In the end we get K is equal to 4.8 times 10 to the negative fifth divided by 0.02 cubed. And that's going to give us actually a nice number of 6.00. And what will be the units? Well, we've got this seconds in the denominator, and this 1 molar will be divided by a molar cubed, and so what we're left with is inverse molar squared. That is the rate constant. Okay, and then the last question, what are the 5 factors which control the rates of reaction? Excuse me, I won't write these down. We have 1, the particle size, 2, the concentrations of reactants, 3, the temperature, 4, energetics slash sterics. So this is things we haven't really covered in detail yet. It has to do with the energy required to initiate the reaction and the orientation that the reaction partners need to be facing as they collide in order to undergo reaction. And then the fifth one is the presence of a catalyst.